Hi guys, in this video we're going to look at section 1.6. If you do section 1.6 and 1.7 out of order, that's fine, not a big deal. But I think because 1.6 it has a lot more algebra and 1.7 is more conceptual, I think it's nice to have the concept up front before we start doing a lot of the calculations. So hopefully you finished 1.7. And for sure, make sure you finished 1.3 and 1.4 and 1.5 before you do this stuff. All right, so let's jump in. It's a pretty straightforward section. I'm just going over the main points. And the first thing we're going to look at are these things called limit laws. So what we've seen three different ways to compute limits, right? We saw how to make a table. We saw graphs, and neither one of those are proofs. Now you can use them to support evidence that you might have about a limit existing or not, but they're not proofs. Then we did the precise definition of a limit, and we saw that even for a simple linear function, it was quite a bit of algebra. And if you go above linear functions, sine and cosine, polynomials, the algebra gets really, really hairy, really, really fast. So we want to find something that we can still use to find limits that is less work than the precise definition from section 1.7 and more rigorous. So in other words, that the methods that we use are more complete. They're less subject to mistakes, right? They're rock solid, you might say. So that's what we want. We want like a rock solid way of computing limits. So we're going to use limit laws. And in order to use these limit laws, the limits have to exist. So if we have these two limits and they exist, we're allowed to combine the functions together to get these limit laws. So here they are. There's a whole bunch. You pretty much have to know them. So the first five here, these are the first five limit laws. They're pretty easy. They follow pretty much logically from what we know about functions. So for example, this is saying, if you have two functions added together, and then you take the limit of the sum, it's the same of the sum of the individual limits. Well, that's how functions work. So that's how limits work. Remember, limits are similar to functions, right? They have a lot of the same characteristics. The only difference between a limit and a function, the main difference, at least the main useful difference, is for us, the limits don't need to, the functions don't need to be defined at this value a, right, in order for a limit to exist. So functions can be defined however you want. And if any of these limits fail to exist, then any combinations of limits fail to exist. Okay, so let's see how that works. Or you just can't say, right? So if you're trying to add two limits together and this one doesn't exist but this one does, then the sum together will not exist. But you could have two individual limits that do not exist and add them together and the limit does. So the idea here is we're really only using this for cases that we've seen before. We're not introducing new types of cases here. We're just trying to simplify stuff we've already done. So sum and difference should totally make sense. Constant multiple is nothing but a generalization of a sum or a difference, right? So if you have a function times a constant, you can pull that constant to the front. Again, that's how functions work, so it makes sense that it works for limits. Same thing here with the product, right? If you have a product of two functions, you can distribute the limit inside the product. So limits distribute inside any arithmetic operations. And of course, quotients, same thing, right? We can distribute that limit inside the division sign. Now this stuff doesn't work if g of x equals 0. In fact, if your denominator equals 0 at a, then the limit law doesn't even apply. You can't even use it, right? Because you're sort of violating, one of the concepts. Okay, so let's just jump right in and do an example here. So we're just going to talk about this example first, The answers, as usual, are on the next slide, but let's talk about them first. So what you have to do is the same stuff you've been doing for the review work that you had to do and the new stuff here. So let's look at, we have f of x plus 5 times g of x. That looks pretty hairy. And the limit here as x approaches minus 2. So go over here to minus 2. So x equals minus 2 is here. F of x, so the function is here, but look at the limit. The limit coming from the right and the left approaches 1. So in order to solve this, we can distribute this inside using our limit laws. But it gets a little more complicated when we get over here to this 5 times g of x. So g of x is here at -1, right? Remember, our x coordinate is -2. So g of x, it looks like the limit is coming in at -1. But then we have that 5. We don't know what order to do this in. Do we multiply by 5 first? Do we do the limit first? So what we do instead is we use the limit laws one at a time. So if you look at this, you can see that we would need to use the addition limit law first, because we need to distribute this limit, in place of this plus sign. Because we can't just plug and go, right? There's too much going on. Now later on we're going to learn when we're allowed to just plug everything in, but for right now we can't do it. So this limit, using the sum law, right? The limit says if I have the sum of two functions, I can distribute the limit inside the sum. Right? Now, this function here, like if g of x is a function, then 5 times g of x is a function. So we're going to go ahead and distribute that in here and then distribute this limit. So I distribute it on the left side and I'm going to distribute it on the right side. So whatever 5 times g of x is, we leave it. So we're not ready to solve anything yet, because we have to keep breaking it down. So we understand how to do the limit of f of x as x approaches -2. We still don't know how to do the limit of 5 times g of x. So we're going to use the constant multiple rule now, and we're going to bring this limit inside, and we can move the 5 to the front, right? And that's what we did here. So this 5 gets pulled to the front. Now we can plug everything in, right? Because now we know what the limit of f of x as x approaches -2 is, right? We found that was 1 when we were looking at the graph. And the limit as x approaches -2 of g of x, we saw that was -1. So this 5, we just tack it on at the end, right? Do all your work on a calculator, right? So that's how you do it. If you have some combination of pluses, minuses, division, just work through them in the order that you're allowed to based on the limit laws. I wouldn't be able to just bring this limit straight inside the 5 because we don't have a rule that says that I'm allowed to do that. And so you might be thinking, well, why did we invent these rules if we're just going to break these rules later? Well, calculus is based on this very firm, very solid foundation of limits. And we really don't, after this first chapter, we really don't spend a lot of time on limits. We use them a bunch the rest of the class, but we don't go back and review, okay guys, do you remember what a limit is? Like, you have to know what it is. So we put a lot of work early in this class into these foundational things, like what is a limit, what are we allowed to do, what are we not allowed to do, when are we allowed to do it, and that sort of thing. All right, let's look at the second one. So, but before we get there, so, right, limit as x approaches -2 of f of x is 1. The limit as x approaches -2 of g of x is -1, and then you just put the whole thing in and you get -4. So notice you're not able to get this just from the graph, and I highly recommend you don't try to do any shortcuts on this, because on a test you're going to have to explain everything step by step by step. Now this is a fairly simple calculation, so I didn't write in the steps. We have some coming up that are much more complicated, and I write in all the steps, and just to show you guys how to do it. But the farther along we go, I'm not going to show every single tiny step of algebra every time. Right? So just for now, just observe kind of how the process works. I'll go into full detail in the next couple examples, and by the end of this lecture, I'm going to show less and less detail as you kind of get the hang of it. All right, let's look at the second one here. Oop. So the second one, we have limit as x approaches 2 of f of x times g of x. Remember, there's no point in trying to multiply the functions together, right? These are just some goofy piecewise defined functions, right? Instead, let's use our limit law and see what happens. So we know we're eventually going to need the limit of f of x as x approaches 2. So here's 2. And the limit of f of x, it looks like it's about 1.5, right? And here's g of x, right, the blue one. It looks like it's going to be 0, right? So when we're ready to plug everything in, we're going to plug in 1.5 and plug in 0. And then we're going to see what it is we're plugging in. So the limit law we used here, this was the multiplication limit law. And it just says if you have two functions multiplied together, you can distribute the limit inside. Now I'm ready to plug in, right? 1.5 and 0. When you multiply 1.5 by 0, you get 0. Sounds pretty good, right? Nothing fancy going on here. At least not supposed to be. Now what if I do f of x divided by g of x? So you look here and you see, okay, it's going to be this number divided by this number. So you're thinking, oh, the quotient limit law says I'm allowed to distribute the limit through the division sign. And we're just going to have 1.5 divided by 0, right? Because that's how the limit law works. I'm allowed to do that. Then you just plug everything in. Now, some of you might be thinking, why did I not write infinity here? Why did I write dne? Well, this is sort of the problem we run into, and this is why we have to have a firm foundation on this stuff. You can't just, think, oh, 1.5 divided by 0 is a vertical asymptote. Vertical asymptotes have limits of infinity. But it could be minus infinity as well. Remember, there's two kinds of infinities that we look at. If this calculation gave me a positive infinity, I would have written down positive infinity. But let's go back and look at the picture and see what's actually going on there. And this is where you have to do some deep diving sometimes. So the idea here is that it's this function divided by this function. No big deal. So as I come in from the right, this function is getting smaller, but it's positive. This function is getting bigger, but it's getting closer to 1.5. So what we have coming from the right is a number close to 1.5 divided by some very small positive number, right? And so on your calculator, you can type 1.5 divided by a very small positive number, and you're going to get a big positive number, right? Okay, great. So that might lead you to believe that the limit must be infinity, right? Small positive number divided by very, very small positive number. So like 1.5 divided by, a very small positive number. You might think, oh, that's infinity. But what happens if we come in from the left? This number is still close to 1.5, right? It's getting closer to 1.5. This number is getting close to a very small negative number. 1.5, or a number close to 1.5, divided by a very small negative number, is a very large negative number. And what ends up happening is that you end up with, when you do the division, as you get closer on the right, the number is a positive number, a very large one. But as you come in from the left, it's a very large negative number. And that's why the limit is written as dne. You need to go through and make sure you're checking all of this stuff. Now, you could have used a table to do this, right? In fact, because you can estimate the values from the graph, and you'll see the pattern, right? You guys already know how to do tables. If you already did the 1.4 and 1.5 activity that I posted, you've gotten your fill of tables. So you know how this stuff works. There were problems just like this on there, right? That if you come in from one side, the denominator gets very small, but it's negative. And if you come in from the other side, the denominator gets very small and it's positive. So if you didn't have access to the graph, this is not enough information, what you're just given here. You can't just say 1.5 divided by 0 is DNE, because there are problems where you might have 1.5 divided by 0 is positive infinity. And there might be other problems later where it's actually negative infinity, the way that we've defined limits. You need to have access to a table or a graph to check all of this stuff. All right, let's keep going. So that's example 1. Not much algebra, but there were some concepts in there, right? The whole rest of these slides, just a bunch of more stuff just like this. So make sure you can explain this, right? Because something like this could appear on a test, and it'll probably be on the homework as well. All right, here's 3 more limit laws. First one is called the power law. And you can see what's going on here, right? It just says if you have f of x to a power, you can bring the limit inside the power. Right? And powers are just repeated multiplication. So that should make sense, right? And that's any number n. If the domain exists, so if a is in the domain, this works, right? If the limit exists. Constant law we've already seen, but I just wanted to put it down as a definite thing. And the most important one that we're going to use in this section is called the substitution law. This is the one we want to get to, right? And if you think about it, it's pretty much what we tried to use in the previous problem, right? If we can get it down to just the limit of x by itself, then you can just plug in a as long as that limit exists, right? So that's why it's called the substitution law. All right, so here's a big problem. So we're going to show all the details using limit laws 1 through 8. So look at what we have here. This is a rational function, right? It's a polynomial divided by another polynomial. And you could make a table, you could make a graph, but those aren't proofs, right? You need to use tools as they come up. So now we need to prove that the limit is what we think it is. Okay, so the first thing we're going to do is we're going to try to distribute that limit so that everything is completely sort of broken apart and all the limits are sitting next to either constants or x's. Okay? And if our limit is next to a constant, then we just write in the number, whatever the constant is. And if our limit is next to an x, we just write in whatever a is. So that's our goal, to break this thing down using these limit laws and then plug everything in at the end. All right, so the first thing we need to do is use the quotient limit law, right? That's the first one. That's the one that says we can break division into 2 different limits. So just look at it and tell me what you think the next one is. You don't have to tell me, but think to yourself, what's the next one? Well, you can't bring it inside that 2. You can't bring it inside that 6. But those pluses and minuses, we have addition and subtraction limit laws that you are allowed to use, right? They're called the sum and difference limit laws. So you can see what's going on here, right? That these limits get distributed inside the pluses and minuses. And we just keep moving them in. If we're allowed to move them in one more step, we move them in one more step. Okay? Because all we're allowed to use, 1 through 8, you have to know the limit laws. These are the only ones we're allowed to use at this stage. We're going to learn more later. And then once we hit the next section, section 1.8, we learn a completely new method. So just make sure you're keeping track of what method goes with what, and you got to learn the names of things. Because on an exam, I can say use such and such method. Use the limit law method to show blah, blah, blah. Okay, next up, we want to bring this limit inside the 2 here, and we want to bring this limit inside the 6, right? And that's called the constant multiple limit law. So basically what we're doing is we're pulling the constants out, right? But now look, something else has happened. Now we have these x squareds. We don't have a limit law for x squareds, right? I mean, if you go back and look at the list, what do we have? We have a power law. So here we have a function to a power. So we can bring the limit inside the power. And that's what we're going to do next. Right? So what we're going to do is we're going to bring this limit inside the square here. And then we're going to bring this limit inside the square here. And that's our power limit law, right? So the reason I marked these up in colors is just so you can kind of track the steps as it goes. But again, this could be on an exam, and you have to break it down just like this, or whatever order works for that particular problem. Now, look at what we have left. Everything is either limit of a constant or limit of x. Once you have that, you can plug all the values in. Right? And that's what we're going to do next, right? So the limit of x as x approaches 2 is just 2. So we plug 2 in there. That's our substitution law. Over here, the limit of 1 as x approaches 2 is still 1. So that's our constant limit law. So we use substitution here, here, and here, and the constant law here and here. And that's how you have to do it until we develop more rules, which we're going to do here in about 2 seconds. But I need you to understand why this works, right? So the first 8 limit laws allow us to do this for many kinds of problems. And then you type in your calculator and you get 3/4, and that's the answer, right? So you have a couple problems on the homework, I think, that ask you to do this, but the online homework can't verify that you're using the limit laws, right? That's something you do on paper. So there are some problems in the book. Those are referenced at the end of the slides here. Just make sure that you're practicing this, because this is important and will be on a test. Well, I can't guarantee it, but it is the kind of thing I like to ask on tests, for sure. Because it shows work, and you can't just Google it. All right, let's keep moving. So we could go on and on and on all day about all the different limit laws. And what you probably thought of while we were doing that last example was, why don't we just combine these limit laws together? You know, wouldn't that save us a lot of trouble? If both laws are valid, isn't the combination of the laws valid? It is. So if we combine number 6 and number 8, we get number 9, right? So what is that? So number 6 and number 8, those are a couple slides back, right? So that's the power law and the substitution law, right? And so the idea is, you know, that when your power law, if you bring the limit inside, if your function is just x, then that's just the limit of x on the inside, which is just a. Well, if that's just a, then this whole thing's just a to the n. So it's sort of like a quicker way to do substitutions, right? And then we have, so number 10 is basically just another version of the power law and the substitution law, right? And of course, we have the root law, right? So the root law is just says the nth root of any function, we can bring the limit on the inside. So this allows us access to a large array of different kinds of functions. And it gives us something called the direct substitution property, which is what we want. We want to just be able to plug the numbers in. Because using limit laws, as you have already seen, is quite tedious, we'd like to move away from that. So, if f is a polynomial, rational function, or an algebraic function, and a is in the domain of f, then the limit as x approaches a of f of x is f of a. Very important. You need to know when you're allowed to use it, and you have to show me that you can use it. So we got 3 examples coming up back to back to back here. That'll get you lots of practice. Because, again, I know how you guys are. I know how students are. I remember being a student. When I first saw this problem, I was like, can't you just plug in 2? Right? Of course I was thinking that. So what happens if you guys plug in 2 here, right? Do you get 3/4? You do. And so that you might think, well, that justifies my use of that rule. It doesn't. Right? You need to have this direct substitution property. So you have to be able to show that for any time you have a polynomial divided by a polynomial, or, like a root function in there, or, a combination of polynomials and root functions, that you're allowed to do this. And the limit laws allow us to do that. Because you might be tempted to use this property when you can't. So let's look at this example, and we'll see what happens, just trying to use the direct substitution property, right? So let's say you decide, oh, well, I can just use this direct substitution property, no big deal. And you try to just plug 2 in, right? What happens? Well, this is a rational function, right? And if f is a rational function, we're allowed to do it. But there's another condition. A has to be in the domain of f. And you look here, you can see clearly that that A is not in the domain, because if you try to plug it in, you get division by 0. So if you have division by 0, all of the techniques we've used up to this point still work if you're trying to show the limit does not exist, or you're trying to show that it's believable that the limit is some number, right? Like infinity, for example, right? So if you think the limit as x approaches 2 of this first function is infinity, you could make a graph, and if you see it just go up like that, that's a vertical asymptote. Vertical asymptotes are infinite limits, right? So we already said you can't use x equals 2. So I went ahead and used a graph just because it looks a little nicer on the presentation. And this is what I got. When I made this graph, the left side goes down to negative infinity and the right side goes up to positive infinity. I don't need a table. I don't need a proof to see that this limit does not exist, right? Clearly that's true. So anytime your left and right side limits are different, your limit will fail to exist. So that's, very similar to what we've done in the past, right? So if we were doing stuff from section 1.5, this is the type of thing we would have done. We would have made a table, make a graph, and that sort of thing. So let's go back and look at the example again. Well, this function right under it looks pretty similar. And so you might think, well, these functions look basically exactly the same. It's just a couple pluses and minuses. How different could it be? Well, here's something that happens in calculus that doesn't happen as much in some of the other disciplines, where you're looking at properties of the function more than any particular value of a function, right? So we have to actually make a graph and say, is it believable that this limit exists? And if it is, we can find it. So let's do part B right here. So I went ahead and I made this on the graphing calculator. So one nice thing about using the graphing calculator, more than an internet graphing resource, is it'll definitely show you if there's a hole in the graph if you zoom in far enough. So my viewing window here is like 0 to 4, I can't remember, 1 to 3. And real clearly you can see right in the middle there's a hole in the graph. So both of these limits appear to approach the same value. That means that that limit should exist, so if we go looking for it, we should be able to find it. So here's how you go find a limit using algebra if you can't just plug the number in. Remember, 2 is not in the domain of this function. So we have to use algebra, right? So like here's our function, right? 2 is not in this domain, so I can't just plug it in. So anytime that happens, if it looks believable that the limit exists and you can't plug the number in, try manipulating what's inside the limit. Or if you need to, you can like pull the function out of the limit, do all the manipulations, and then put them back in. That's what we're going to do for the next example because it's a lot of algebra. And I kind of, You don't want those limits moving around. It's just too much writing. Or in my case, too much typing, right? So I factored the numerator. Because I know if there's a hole in a graph, that tells me that there's some copy of the denominator sitting in the numerator somewhere, right? That's what a hole in the graph tells you. Like this kind of hole without an asymptote, right? So I tried to look for a factor of x minus 2. Turns out there is one, right? When you factor this polynomial, this is what you get. And that didn't work for the other one, right? For the first function we saw, it didn't factor. Well, you can cancel these x minus 2 terms, and that just gives you the limit as x approaches 2 of x plus 3. So here's the thing. You have to convince yourself, is this graph the same as this graph when it comes to limits? And it turns out, pause the video if you're not sure, turns out it is the same. Remember, limits do not require that this function is filled in at that point A. So we're allowed to have a hole here. So whether we replace this function with the identical function with that hole filled in or not doesn't make any difference when it comes to the limit. But, as we've seen several times, you don't want to do tables, you don't want to do graphs, you don't want to do epsilon delta proofs every time. You'd much rather find a method that's, algebraically a little easier. And this is it, right? Now we have this other function that's the same as this one, except that little hole's filled in, which doesn't change the limit. And now I can use direct substitution, right? Because now x equals 2 is in the domain of the blue function here. And it's a polynomial, right? It has to be a polynomial, rational function, or an algebraic function, right? Because that's the only thing the limit laws gave us. So think about that. And just remember, there's no way to know ahead of time which one it is, right? You can try to factor it. If it doesn't factor, try to graph it. Because remember, if it's a rational function and it doesn't factor, there will be a vertical asymptote somewhere. So your answer is either going to be, plus or minus infinity, or does not exist. Right? If you're trying to divide by 0, right? If you try to just plug in 2 here into this denominator. There are some trick problems you can watch for. Like if this limit says limit as x approaches 4 or something. Well, 4 is in the domain of this function, so you can plug that in. So don't always assume that you're trying to simplify it. Try to plug it in directly. If you get division by 0, you have to stop and you have to try a different technique. All right, let's move on. Oh, there's the answer. Sorry, I forgot to put the answer up. Right, so you have, limit as x approaches 2 of x plus 3. Well, it's a polynomial. You can plug the 2 in, so you get 5. Now, we already knew it was 5 because I had a graph. But a graph still is not a proof, right? We're only looking at problems that have relatively nice solution methods. Now, you might disagree after you see the next example, but these functions can get real complicated real fast. I'm just picking examples that are complicated enough that you need to use different techniques, but they're not so crazy that you get overwhelmed with trying to keep track of the different techniques. Okay, moving on. And that brings us to this thing called a useful fact. And we just saw that it's believable, right? So the example we just did showed us it's believable, right? That replacing a function with a simpler one doesn't change the limit if the functions are equal everywhere except a certain point, whatever that point is, right? A. So what this says is if the two functions are equal everywhere, except where x equals a, right? I mean, because they're not required to be the same at x equals a. But if they're equal everywhere when x is not equal to a, and the limits exists, then the limits are the same. And that just came from this problem here, right? We replaced a linear function with a hole with a linear function with no hole and got the right answer. This will always work. So that's why it's a useful fact. So this is our goal, to use this formula, to use this useful fact. All right, let's do some of these. So I'm going to go through these fairly quickly. All of them have a bunch of algebra. There's a variety of techniques in these three. You're going to want to go through these on your own, at your own speed. But I'm just going to walk you through it real quick. I'm not going into a big explanation about them. They're pretty straightforward once you get the hang of them. And this is sort of a glimpse into the world of what we're going to be doing once we start chapter 2. We're going to do problems that look like this. All right. In fact, this one right here is basically a problem from chapter 2, part C. Let's look at the first one. Evaluate the limits if they exist. So, as I said before, you want to try to plug the number in first. So you have t approaching 5. So you try to plug in 5. 5 minus 5 is 0. You have to stop. You can't divide by 0 ever. So that means we have to do some algebraic manipulations, right? So we're going to simplify the expression in order to find the limit. So the first thing we're going to do, so I pull the function out of the limit. You're allowed to do that. And then once we simplify it, we're going to put it back in the limit, okay? So the algebra technique we need here is multiplying by the conjugate. So you look for the radical. The radical will either be in the numerator or denominator. It doesn't matter where it is. There's only going to be one radical. And you flip the sign, and you multiply by that value on the top and bottom. What that'll do is it'll get rid of the radical. Now what we do, it's on the next slide, but I just want to point out where we're headed with this. I mean, it's on the next little pop-up there. We're going to be foiling this numerator. We are not going to foil the denominator. Trust me on this. I teach this class a bunch. People like to go crazy with foiling because they're like, oh, it's this thing I learned, so I need to use it. We're trying to cancel that t minus 5 out of the denominator. If you foil it in, then you can't cancel it. Leave it out so that we can foil it. I'm sorry, that we can cancel it when we need to cancel it. So we foiled the numerator, right? And you can see how that works, right? So this is just difference of squares, right? So you have like a minus b times a plus b is just a squared minus b squared. So radical t plus 4 squared is just t plus 4. And then minus 3 squared, which is 9. So we foiled the numerator. We don't mess with the denominator. Just multiply it across. You need parentheses. Now we're trying to cancel this t minus 5. That's our goal. It's what we want to do. So this simplifies to t minus 5. Just cancel those t minus 5s. You get a 1 in the numerator. And you're left over with just part of that conjugate in the denominator. So what have we done? That means that this function here is the same as this function, except for 1 point, right? This has a hole in the graph somewhere at 5. This doesn't. That's it. That's all we've done. We've removed the hole. Now, the original problem called to find the limit of this. So I'm going to evaluate this limit by plugging this number into the limit. And that's what this says here, right? So the original problem was this limit. Well, I can plug in this other function. I can plug in this one right in here. And now to evaluate this, we again try to plug in 5 into where t is. Well, 5 is in this domain. That means we can plug it in using direct substitution, and we get 1/6 as our answer, right? Just do it on a calculator or do it in your head. I don't mind. Either way. This is a pretty typical problem for section 1.6, and we're going to see stuff like this again in section 2.1 and 2.2. It's a bunch of algebra. Anytime you see a radical, you're going to need the conjugate technique to solve it. do not distribute any of the stuff that you're hoping will cancel. Okay, we want to cancel that t minus 5. Don't distribute it. You need it to stay out so that it'll cancel on its own. All right? So one thing I will point out to you guys is you might want to pause the video and run through this problem again right now without looking at the answers and see if you can do it. Because this is what the homework looks like. This is what the tests are going to look like. This is really important that you're able to do it. I'm moving on, but you can pause it. All right, so the next one we're going to look at, the next problem, is this one. Again, we want to plug in 5. We can't. Right? You get a 0 in a denominator. So we're going to use the same approach, right? This is actually the same problem we saw in the first video. Well, the first content video, not the tech video. And we used a table of values to estimate the limit. So let's actually prove that this limit is correct using direct substitution. So first thing you do, of course, is factor that numerator, right? We're trying to cancel that x minus 5. So the first thing you have to do is find the common factors. Because you look at it, you look at 4.9x squared minus 122.5, and it doesn't look like it factors, but it does. And it's a lot easier to factor out 4.9 than it is to factor out x minus 5. So factor out the common factor first, right? We can see 4.9 is in the first term. Just take a calculator, do 122.5 divided by 4.9, right? So you factor that out. Then we completely factor the numerator. Now it's a little easier to see. We're trying to get rid of this x minus 5. Factor that numerator. These two will cancel. And you get a much simpler function. So if we want to find this limit as x approaches 5, that's the same as finding this limit as x approaches 5. So we just set those equal to each other, right? So if I'm trying to solve this, that's exactly the same as trying to solve this. This is a polynomial. So I can plug in 5, I can use direct substitution, and 49 is my answer. So another thing I want to point out, don't be in a big hurry to simplify a lot of these. One thing I like to do is do all my simplification steps together, usually at the very end. Because you might see this function here and go, well, can't we make that 4.9x times 14.5 or whatever? No, what is it? 19.5? 20. Hold on a second. I'm good at math. I'm just not good at arithmetic. 4.9. Yeah, 24.5. Yeah. Can't we just distribute this and make it 4.9x plus 24.5? Sure. Did that save you a lot of work? Not really. Look down here. I'd much rather add 5 plus 5 and then multiply by 4.9, as I can do that in my head. Don't need a calculator for that. So you see the idea, right? You're not in a big hurry to simplify anything. Just carry the steps down, keep track of your work. When you're writing stuff down on the page, work vertically. Try to be real vertical. It helps a lot. It's another reason I like to use PowerPoints, because it kind of confines you to a single space, kind of forces you to work vertically. So, same as the last problem. I'm moving on. You might want to pause and do that problem again, just to make sure you can do it. Part C. Let me go back here. Right. What is this horrible monstrosity? Who put these negative exponents in my math problem? Same sort of thing, right? Try to plug in h equals 0. Got a 0 in a denominator. What can we do? Well, we're going to do exactly what we've been doing. We're going to use algebra to solve the problem. All right, so the way that I instruct you guys to do this is negative exponents are not anyone's friend. It's hard to do algebra with exponents as it is. So you want to rewrite those exponents as fractions, and you want to pull that 1 over h to the front. Because if you don't, you're going to end up with like a stacked fraction, and stuff's going to start moving around and get all weird. That 1 over h, that h is what we're trying to cancel. So if we're keeping it out to the front, it's not getting in the way. Just leave it out there. It's fine. It's not going to hurt anything. Plus, it just looks nicer. Plus, I have to grade your tests, right? So this is an easy way to grade it. So what do I do next? I need to simplify this expression so that I can cancel this h. Well, this is a subtraction problem, so I have to get a common denominator. So the common denominator is going to be 3 times 3 plus h. So you just multiply both by 1, right? 3 over 3 is 1. 3 plus h over 3 plus h is also 1. So I'm taking both terms, multiplying them by 1, which you're allowed to do. It doesn't change the value of a fraction when you multiply it by 1. And then I distribute, right? So 1 times 3 is 3. Minus 1 times 3 plus h is 3 plus h, and the denominator is 3 times 3 plus h. Now I'm ready to subtract, right? So the 1 over h is still out front, so now I have 3 minus 3 plus h in parentheses. Don't forget to distribute this negative, because if you don't distribute the negative, you're going to get the wrong answer, right? So just watch out for that. So now we're here. So 3 minus 3 is 0. We have a negative h, right, which is here. This denominator doesn't change. The 1 over h is still there. And then we cancel the h's. So negative h and h cancels to negative 1. And now we're ready to plug these in. So this expression here is equivalent to this expression here. So we want to find the limit of this as h goes to 0. That's the same as this as h goes to 0. And the rest of it looks like stuff you've seen before. So this is the way that I suggest that you do it. Oh, got to circle my answers just like on a test, right? So I'm not saying this is the only way to do it. In some ways, I show more detail than some people. In other ways, I show less detail. It's up to you how much detail you want to show. But your job in this class is to get answers right using methods that we've discussed. So this is probably the safest way to do it. You don't have to annotate. You don't have to, like the comments that I have in colors, you don't have to write those on a test. I'll be able to follow it. And in fact, when you get to a problem that has as much algebra as this, a lot of times I won't even annotate it in the notes, right? I'll talk about it in the video. I'll go through it in the video and tell you where everything came from. But at some point, there's just a limit to how much information on a screen you guys can handle at any given particular time. Now, I know there's a long video. This is definitely one of the longer sections we do this semester. But got one more example in the section. So we have two theorems here. I'm not proving either one of these, and we're going to combine these two theorems together to make another theorem on the next slide. So what is this saying? This is saying that if this limit exists, then the limits from both sides exist and equal the same number. And you're thinking, well, yeah, duh, we defined that way back in section 1.5. That's true, but here we're calling it a theorem. So this is something I could prove. And if I had a little bit more time in this class, I would prove it. But I'm not going to. If you guys ever are interested in seeing proofs, let me know. I can show you where to find those, or I can make separate videos for those. But if I don't go over the proof in the notes, then you don't have to know the proof. Now we have another theorem that says if f of x is less than g of x when x is near a, and both limits exist, then the limit of f of x is less than the limit of g of x. So really what this is saying is that if you have two functions that are equal and you tack on limits, they stay equal. But this is much more general, right? It's saying if a function is less than another function and you tack on limits anywhere near that point, then the limit is going to be less than. So what this is really saying is that, and when we say near, is this is based on that epsilon delta concept. So even though we're learning these in the reversed order, right? We did section 1.7 first. It's kind of easy to see after doing the epsilon delta proof why this works, right? Because if f of x could somehow switch with g of x, then it wouldn't be within the rectangle of the epsilon delta, right? Again, we're not proving this one. Sorry, I just bumped the mic. Yeah, we're not proving this one, but it should be believable, right? In fact, we got a nice picture here. This thing's called the squeeze theorem, and it's a nice picture of why this should be true. So the squeeze theorem is about three functions. That if you have g of x pinned in between f of x and h of x, near a, notice like away from a, it can cross, right? But as long as, like, as we start getting close to a, at some point, they can't cross anymore. Then these limits, we can apply the concept of the limit. So look here. F of x is less than g of x. F of x is also less than h of x. And if the two outer function limits are the same as x approaches a, then g of x is trapped in between those functions and has no choice but also to have the same limit. This is also called the sandwich theorem. You can see why. The squeeze theorem is used a lot. Many of you, I read some of the survey results, and I can see a lot of you guys are high-end science majors, about half the class, computer science or natural science. So you guys are going to have to go on and take much more advanced stuff. For you business folks, you're not really going to see the squeeze theorem very much in like a high-level econ class or something. I mean, occasionally, maybe. But it's used a lot in Calc 1, and we use it a lot to prove things about other functions later on. It's actually quite useful. So make sure you guys understand what the squeeze theorem is saying, because you have to use it sometimes. You don't have to prove it, but you have to use it. It should be believable, though. Just looking at it, right? It should make sense that g of x, once you get close enough to a, it's not allowed to jump out of there. It's not allowed to cross. It has to stay in between. And if you get sufficiently close, which again we already did section 1.7, so we know what sufficiently close means, that it's going to stay trapped. And if the end limits approach L, then g of x also has to approach L. So let's use the squeeze theorem to evaluate this limit. So let's look at it. Your first thought should be, I'm going to plug in 0. It should be, right? Because this is a polynomial, so you can plug in 0. So this limit is going to be 0. What's this limit? We don't know, right? This is one of those real wiggly ones. So what happens when you have 0 times a wiggly thing? Which one wins? Does 0 win or does the wiggles win? Let's find out. So the strategy we're going to use here is to start with a statement that you know to be true and then use algebra to solve the problem. So what do we know about... So we know everything we need to know about x squared, right? We can just plug 0 in, we're good to go. We don't know anything about cosine of 1 over x, but we do know something about cosine of theta. So cosine of any number is pinned between -1 and 1, right? That's the range of cosine. So no matter what, cosine of 1 over x is going to be between -1 and 1. So that's just the only fact that we really know about cosine that we can use. So we just write it down. Then you say to yourself, can I make that middle function look like what I'm trying to prove? Well, sure, let's just multiply through by x squared. So if we multiply everything through by x squared, now that center function is what I want it to be, right? Now let's tack on those limits. So we're allowed to tack on these limits because we're using theorem 1.6.2 twice, right? So let's go back and look at the theorem, make sure you know what you're doing here, right? We're using this theorem twice. We're using it for f of x and g of x, and then g of x and h of x. So we're just using 2 copies of the theorem that overlap at g of x, right? And so whatever's true about the function is true about the limits, right? So, you know, here's one copy of the theorem, and here's the other copy of the theorem. So we just tack those limits on. Now the middle looks exactly like what we're trying to prove. A lot of times I'll use parentheses and braces just to like clarify what you're seeing in the notes. You guys can use combination of brackets or braces, parentheses. I don't care what you use. Well, here's the thing. We know what this limit is on the left side because this is a polynomial, so we can plug it in, right? Direct substitution says we can plug it in here. This is a polynomial, so we can plug it in. Let's do that. We know what both of those are, right? Direct substitution says I can plug both of those in and get 0. So what do you think the limit is for the center function? It's a number between 0 and 0, with the endpoints included. So it has to be 0, right? So we just proved that the limit of this function is 0 without knowing anything about the function. Because cosine of 1 over x is very wiggly, and it gets more and more wiggly the closer you get to 0. So we don't know. A graph would not tell us exactly what was going on here. This is a proof, so now we know exactly what's happening. So if you're interested, I didn't put the graph in the notes. Go ahead and graph the function, and then graph negative x squared and x squared all together, and you'll see what happens. Right? It looks really cool. You have a problem on the homework that resembles this, so you'll be able to do it then if you don't want to do it now. All right, well, that's it for the notes for this section. Next section, we're going to do section 1.8, which will end chapter 1 for us. As before, lots of book exercises if you need extra help, videos and animations in the media index. The homework tutor has step-by-step instructions. Some of the ones that are on the homework have step-by-step instructions in their videos. Can't beat it. Check it out. And of course, you can always use the recommended free internet resources that I suggested. If you guys ever find other internet resources, feel free to run them by me. And if they're good stuff, you can post them on the discussion forum so other students can use them. So that's it for today. And I'll see you guys next section. Bye-bye now.